So u-substitution can be used as an integration technique, whether it's with an indefinite or with a definite integral. And it's actually super nice to use with definite integrals because it makes the math usually like way easier. So we're just going to do two examples to kind of show how to do this. So the first thing I want to say is, right, if you're looking at this function, there's a lot of craziness going on in the denominator. You could think, oh, well, I can easily square out 1 plus the square root of x, and then I can multiply by that by the square root of x. But the tricky part here is that everything's in the denominator, so you don't actually want to do that because then you're going to make it more difficult. So having it like factored down like this super nicely makes it pretty easy to actually recognize. So this is where being really good at derivatives really helps out with integrals, because you really can't be good at integration until you're really solid on derivatives because they're just backwards of each other. So you want to be able to recognize when you have the derivative. Like if you take one piece of it and take the derivative of it, you want to be able to recognize that that derivative pops out in a different place. And this is what I mean. So the most complicated portion of this function structure is the stuff that's inside the binomial that's being squared. Right, so we have, I'm going to let u be 1 plus the square root of x. So that replaces all of this stuff. So now I need to make sure I can replace my dx, and I have a square root of x in the denominator that's outside. It's going to work out really nicely. So if I take the derivative of both sides, right, remember that this is just x to the 1/2. This becomes 1 over 2 x to the negative 1/2 dx. So du is just equal to dx over 2 times the square root of x. Well, hey, got a square root of x in the denominator, right? I got my dx taken care of. Just got to get rid of that pesky 2 now. So if I multiply both sides by 2, now I know that 2 du is just equal to dx over the square root of x. So now here's where the definite integral part comes into play. These are in terms of x values. So you have two options for how you proceed. So option kind of 1 is that you could say I'm taking the integral from x equals 1 to x equals 9 of my 2 du, right? So my 2 du, I'm going to put that up here, right? So that's going to replace my square root of x in the denominator and my dx to the end over u squared in the bottom. But like that's a little bulky looking because I have x equals on my limits of integration and I have a u inside my integral. Now I can totally do it like this. I can integrate this the way it is, and then I can resubstitute back in for what the u was in terms of x, and then I can plug in and solve. Well, why, right? So what I could do is say, well, if x is equal to 1, then u is equal to 1 plus the square root of 1, so u is just equal to 2. And then if I say x is equal to 9, that just means u is equal to 1 plus the square root of 9. Well, that's 1 plus 3. U is equal to 4. So I could say that this integral is really just, oh my gosh, the integral from 2 to 4 of 2u to the negative 2 du, just rewriting it real fast. Because if I do that, I don't have to write the x equals on my limits of integration anymore because everything's in terms of u, the same variable. And now I don't have to switch everything back to x's at the end. So if I do it this way, now I can just integrate. So this is 2 times u to the negative 1 over negative 1, evaluated from 2 to 4. So that's negative 2 over u, evaluated from 2 to 4. So that's negative 2 over 4 minus negative 2 over 2. It's going to be negative 1/2 plus 1. Well, that's just equal to 1/2. So I never had to go back to the x's. I could just plug in for where I was with the u's, solve from there. Let's do one more. So this one's going to kind of combine a couple of different u-sub strategies. So I'm going to take the integral from 1 to 2 of x minus 1 times the square root of 2 minus x dx. Okay, so right away we can kind of clue in that this is definitely a u-sub because we have the product of two things and one of those is trapped inside of a square root, so we can't really bring it to the outside. So because there's stuff inside the square root, that's probably going to be my u, so I'm going to go ahead and replace that. So if I take my derivative here, I get that du is equal to negative dx, which means that negative du is equal to dx, okay? So I can replace this guy now with negative du. And then I need to replace x minus 1. So if I take my u and redefine it, I can switch this to be, well, x is just equal to 2 minus u. So then if I subtract 1 from both sides, x minus 1 becomes 1 minus u. So now I can replace this with 1 minus u. And then we have to replace our limits of integration. So if x is equal to 1, u is equal to 2 minus 1, so that's a 1. So this one stays a 1 on the denominator here. And the top one, right, if x is equal to 2 is my top limit of integration, u is equal to 2 minus 2, so this is going to equal 0. Right, so if we take this mess and kind of consolidate it, we're going to take the integral from 1 to 0 of 1 minus u times the square root of u times negative du. So I want to switch the limits of integration, which I can easily do here, right, because this is negative. So remember, when you have a negative of an integral, you can just flip the limits of integration. So that's going to be from 0 to 1 of 1 minus u times u to the 1/2 du. Ooh, that looks like a W up there. Let's fix that. And then I'm going to distribute that u to the 1/2 first. That's u to the 1/2 minus u to the 3/2 du. Integrate real fast. That's going to be u to the 3/2 times the reciprocal minus u to the 5/2 times the reciprocal from 0 to 1. So that's going to be 2/3 times 1 minus 2 to the 5th times 1 minus, that's all going to zero out. So that's really going to be 10 minus 6 over 15. So my final answer here is 4/15.